I am discussing in this discussion forums or the other TAs are doing, those will help you to tackle the assignment problems. And based on the assignment problems, whatever we are discussing and whatever the professor has covered in the lectures, all will be mostly covered to be, and all of them will be discussed in forms of question, introduced to in forms of question in your exam. Does that answer
Okay,
your
sir.
question?
Oh, yes, sir. Sir, sir, light, sir, can you, sir, it will come on some questions, like topic wise, it will come on exam, no, sir? Like,
In the
some
final
questions are
exam,
teach.
you will have questions from the topics that are discussed in this course only. Okay.
Sir, like assignment questions, no, sir. Like, sir has given assignments, no, sir. Those questions have been come on exam. Like,
Not exactly, maybe somewhat different, but around those questions you should prepare.
okay, sir. Exam questions plus sir has taught, sir what he has taught, being we have to prepare that, like that.
Exactly. Because your assignments are also, if you have seen that assignments are also based on the topics he had covered in the lectures, right?
Sir. Yes, sir.
Okay.
Okay, sir.
So, okay. So, Ankit, you asked me that question about the collector doping last session, right? If I am not
Yes, sir.
mistaken.
Yes,
So
sir.
I have, if you have, did you receive the YouTube playlist link and the lecture material link, discussion sessions material link from the NPTEL team?
Yes, sir. Yes. It is in the part where we are getting the lecture. We're getting the lecture. There is
It
separate.
is there in a separate Excel sheet, right?
Yeah. Yeah.
So if you go to the lecture 2 material on the YouTube, there is one comment from me. And I think there is only one comment in that video. So there I have posted one material, one PDF, open source PDF, where you can get the step by step, process of how that vertical BJT is fabricated. The bottom one, the P plus region or the highly doped region, is basically done with your diffusion process or normal dopant diffusion to a pristine silicon wafer. Okay. And the lower doped portion on top of that is done by some method called epitaxy. So you have multiple methods to do epitaxy or epitaxial layer growing. One is your chemical vapor deposition, another one is your molecular beam epitaxy, and there are other sophisticated methods that are used in today's technologies. Okay, so a comprehensive overview of that BJT fabrication is given there. So I suggest you to go through that. If you have any further question, you can directly email me. We can discuss over email, or I may introduce a short video for that. Okay?
Okay, sir. Thank you.
Okay.
Actually I don't have the time for that to check. So I will check and I will get back to you, sir.
No, no, sure. You don't have to check right away. You can check at your leisure, and then you can
Yes, sir. Of
get
course, sir. Of
satisfied.
course,
Okay,
definitely.
sure. Okay, so welcome everyone. So this is week 3, NOC 25 EE110 NPTEL tutorial session on microelectronics devices to circuits. The course instructor is Professor Sudeb Dasgupta. I am one of the TA of the course. I am Debashish from IIT Kanpur. So as you know that we go live every week from 7 to 8 on Saturdays. So I think this you guys are accustomed by now. So I'll just skip. So this is the okay, so this is week 3, right? So this is the question where I left last week. So I have introduced the question and asked you to think about it, right? So any of you did any one of you find time to look into the question and think about it? Why the two, the question is basically in a BJT transistor, two PN junctions are connected back to back, right? And that provides me the amplification or the transistor action. So why the same amplification I cannot achieve by connecting two separate P-N junction diodes and just breadboarding them in a fashion that is shown in the right hand side picture. Okay, so this works, this does not work. So you have to tell me why is it so. Anyone want to volunteer? So the concepts that are required to answer this question, I have already introduced in last two sessions, right? So you should be able to actually answer this question. So first tell me that what is the transistor action?
There should be some transfer of resistance.
There should be some transfer of resistance. That means you should be able to control basically what transistor action implies that you should be able to control the electrical characteristics of one terminal by means of other terminal. Okay, so this is your controlling terminal or controlling port. This is your controlled port. So in case of BJT, so if I draw a BJT, so what is that we are trying to control? What is that we are trying to control and what is controlling that? One question I had discussed that answers this question, the answers this. Anyone? So it is NPN in the question. So this is NPN. Okay, emitter base collector. So anyone want to volunteer? What is the, so what is we want to control?
IC.
So this is my input port, right? And this is my output port. So I want to control IC. So I want to control my IC. And by what means? What is the controlling?
VBE.
So VBE or VEB is the controlling agent and IC is the controlled, right? So for an amplification action, what we want, that a small change in VBE should be giving me a large change in IC. If it is to be happening in the same, between the same two terminal, then it is not transistor action. It is just your nonlinear resistance that we have discussed. Okay. So for transistor action, for getting that higher IC, what is the fundamental thing that we need to ensure in the BJT? For examples, electrons are traveling this way, right? This will come and eventually this will go to your collector. But in between, there are places where these electrons will go and recombine with the holes, right? So for a good amplifier, what do we need? One, we need to bias it in the forward active that we have discussed. And what does that mean? Your this junction is in forward bias and this junction is in reversed bias, right? So what happens when my this junction is forward biased EBJ? Electrons will get injected from the emitter, and as soon as it reaches my P side, for example, as soon as it reaches this point, so what is electron in case of what this is the motion of electron, right? The red line is the motion of electron. So what is electron in p-type base? Is it majority or minority?
Minority.
So how will that minority carrier move in the p-type region? The question is, how will this electron move in the p-type region?
By recombining with electrons.
By recombining with holes, right?
Also, sorry, holes.
So if it recombines with hole, what will happen? The concentration of that electron will reduce. Whatever excess electron that is coming at this point, this concentration, if you plot with respect to distance, so this will reduce basically exponentially. This we have seen, right? At this point, this is, let's say, delta n p0, or your excess electrons. Delta n defines denotes excess electron, p subscript denotes in p-type region, 0 denotes at the position, at the just at the depletion edge. So it will recombine, or its concentration will decay with respect to space, with respect to your distance, right? So then tell me, to get these electrons through to p side, or or n type collector, what should be the condition? If all my electrons recombine in the p type base, how many electrons will reach the collector? So if all the electrons are recombined between this portion, so how many electron will reach in the collector?
No electron will reach.
So that means what? That means I do not get any collector current, right?
Yes, sir.
That is not an ideal situation for any sort of transistor action or amplifier. Transistor action will still be there, because then also my resistance will change, but amplification will not happen. For amplification to happen, I want all of my electron, most of the electrons that are injecting by the emitter, should traverse through the base region and reach the collector. Fine. So
Yes.
the condition is, all of the electron cannot recombine in the base region. So this leads us to do what? This leads us to make sure that my width of the base region is reduced. These are the design constraint that this phenomena puts on the fabrication guys. Okay, they need to make sure that the base width is very little, so that the recombination is lower in the base. And what are the other constraints? That my n of E should be much more than n of B, or the concentration of emitter should be much more than the base. That means this will ensure what? This will ensure that my this quantity, this delta NP0, the starting quantity for the excess electrons in the p-type base is higher. Okay, and how it will be higher? For example, my this is Ne is 10 raised to 18, and my Nb is 10 raised to 16. So what is the number of electrons in this? 10 raised to 4, right? And here 10 raised to 18. So at the starting point, you always see this will be somewhat dependent on how lowly doped my that region is, where it is becoming a minority carrier. Okay. So summary of the story is that my electron, I need to reduce the recombination, and obviously all of the electrons cannot recombine. Now tell me what is happening in case of two p-n junctions. Now let's say I am connecting two P-N junctions. This second case. This is first case that we have discussed here. Now we are discussing the second case. So this is N, P, P and N. First of all, tell me how many junctions are there? Anyone? How many junctions are there? So how many junctions are there
Three.
in this structure? This is one junction. This is one junction. And do you see any other junction?
No, sir. No, sir.
There are junctions. Okay. This is a junction. This is a junction. These are called metal semiconductor junctions. Okay. So the way these junctions, the YOLO junctions create PN junction diodes, these metal semiconductor junctions creates two types of thing. One of the two types of things. Either it will create a resistance or we call it an ohmic contact. So basically this is your metal semiconductor junctions. Metal semiconductor junction. Okay, it can be of two types. Either it can be ohmic or it can be Schottky. Okay, so you heard about Schottky diodes, right? Anyone? Have you heard of Schottky diodes?
Yes, sir.
So those Schottky diodes are nothing but your metal semiconductor junctions. It can be metal P type, metal N type. Okay. So, but when it is ohmic, it is nothing but just a resistance. So these junctions are basically ohmic. Now tell me how many junctions are there in this case 2. In this case 2, I have two PN junctions and additionally I have these junctions. Okay. So these junctions and these junctions. So the metal is coming from the wire. The metal wires you are connecting for emitter and base, emitter, base and collector. Okay. So now tell me what will happen. Now let's say I forward bias this one. What will happen? Emitter will start to inject electrons, right? The same type of action will happen and this will reach this point, this green point in this case. Then these electrons will become minority carriers and diffuse through this. Fine. But what is the scenario in case of the excess electrons? How will your excess electrons behave? Excess electrons will again decay exponentially, but whenever it is reaching this metal semiconductor junction, no, it has to be zero because metals have infinite recombination centers, or in a sense you can think it in this way. Suppose how many for in 1 centimeter cube in this place, let's say you have 10 to the power 4 electrons. Okay, at this place let's say whenever you are crossing the base region and whenever you have reached the end, it becomes, let's say, your 100 electrons per centimeter cube. But in case of metal, how many electrons are there per centimeter cube? We have discussed it in the first lecture. Just tell me the order. It is around 10 to the power 22 electrons per centimeter cube. So do you see that this 100 electrons per centimeter cube find any significance when it reaches 10 raised to 22 electrons per centimeter cube? It is equivalent to saying that the number of electrons at this point or the number of excess electrons in this point is equal to 0. Fine. So what you are doing, you are adding 10 to the power 22 plus 10 to the power 2. So what will this sum will be? If you take 10 to the power 2 common, so it will be 10 to the power 20 plus 1. Do you see the change of order? So it will be nothing but your 10 raised to 22. Okay. So ideally, so essentially what is happening is that at the whenever the PN junction is finished and connect to a metal wire, the excess electrons that is traversing in the base region or the minority electrons that is traversing the base region, all of them gets recombined. Okay. When all of them recombined, then how many electrons are reaching the collector? How many electrons will reach the collector? Because this junction is your reverse biased, right? Anyone? All of the excess electrons that was injected from the emitter region to the base region are recombined at the intermediate metal wire that you have put. This is the this metal wire, this metal wire. So all of the electrons are recombined, minority carriers. So no electron will reach to the collector. Basically, you are getting no current out of it. So obviously there will be no question of amplification, right? So basically in this case, no electron reaches collector and essentially no amplification. So do you see the difference between the two cases?
Yes.
So what I will suggest, those who are in undergraduate or if you have lab access in your postgraduate, just go to your electronic circuit lab or analog circuit lab, take out the component, connect to a breadboard and oscilloscope and see that this problem in practical. Okay, just check out that if your, I think you all have done at least one amplifier breadboarding in your undergraduate. If not done, please do this exercise. Connect the NPN transistor and see if that small signal is getting amplified here, and connect two diodes as shown in the diagram and see if there is any amplification. Okay, you will get to understand what is happening. Fine. So let's move on. Next question is, the base current is always the, can anyone answer?
Smallest one.
Why do you say so?
Because less recombination occurs in the base regions.
Base current is always the smallest one. And you tell what is the question? Smallest is the smallest one. And you tell me that why, what is the reason you have mentioned?
Less recombination occurs there.
less recombination occurs there. Okay, but only recombination, only do you think that recombination is the only current component of the base?
No, sir.
Then
Also, the
what is the
hole
other
contributes to
component?
it. Holes also contribute to it.
No, recombination means your electrons and hole both will take participate, right? Electron
Okay,
cannot
sir. And
recombine by its own.
yes, sir.
So what is the other
And
current component?
more number of electrons enters into the collector region, sir, due to the small width of the base.
No, that is one aspect of it. You are telling the same thing. That the base region width is smaller, that means the recombination will happen lesser. But my question is, what are the current components of the base? That you should be aware of before answering this question, right? Is recombination current the only current component of the base? You are saying no. So tell me what is the other current component, okay?
Diffusion current component.
Diffusion current component, can you please elaborate on that?
Because there is a for p region the electron is the minority, or if you take a PNP, so for n holes are the minority, and for p
Right.
holes electrons are the majority, and for so holes will flow through the PN junction due to that gradient of concentration, so it will also create an current component.
So basically you have this and you have this, right? So this is what current? This current is your IE. Fine. This current is your IEP. This current is your IEN. This current is your IBR. And this current is your IB. And this is your IC. Is the current, are the currents okay? So what is the your base current? IB. IB is composing of what two currents? One is your IBR and another component is your IEN. So Manoj, is it clear now? There are two current components in the base.
Yes, sir.
One current is the recombination current, that is this current that you have mentioned, and this is the current that determines how many your basically how many of your remaining electron remaining holes are traveling to the collector region. That is what you have mentioned. But the other component is that you have a backward injection current, right? This current. So basically it is a PN junction. If you forward bias it, the P junction will inject holes towards the N side, and N junction will N side will also inject whole electrons towards the P side. So the current, if you studied in PN junction, is composing of two components, the electron current and the hole current. So you have by default assumed that your I you have assumed that your IEP is much larger than your IEN. So this as if there is no this current in your answer, and that is true. This actually happens, but there is something that enables this. What is that thing? What is that condition? This is enabled by doping of emitter is much higher than doping of your base. Okay, if base is lightly doped with respect to the emitter, then obviously base will inject lesser number of electrons in the p side emitter, right? So
Yes,
this
sir.
is one condition. Another condition is the recombination current is lower. And what are the measure we take for recombination current to be lower? What are the design aspects?
Base width to be low.
Exactly. So your WB has to be lower, right? Because your area will be same. If you take the 3 dimension, everything will be same in the for emitter base, and this dimension is same. This is the your width dimension, or let's say your thickness dimension. Okay. So this length we need to reduce short base diodes. So these are the two reasons, or these are the two design consideration for which you say that your IB, the IBR and IEN, both components are lower. So that is why it is the lowest current component. Okay. So please don't ignore this quantity, because suppose if you have given a doping profile, some arbitrary doping profile, then you will be in trouble. Okay. If I say that this is your 10 to the power 15 and this is 10 to the power 18, then you cannot say that your base current is the lowest current component. Okay. So recombination is one aspect of it. Another aspect of it is the backward injection current. Okay. So that is done. Then let's move to the next question. So let's take a NPN transistor. So this is NPN. Beta is given as 60. By the way, can anyone tell me what is alpha and what is beta?
Alpha is common base current gain and beta is common emitter current gain.
Common base current gain, and beta is common emitter current gain. So you understood, right? As soon as beta is given, so I immediately draw the common emitter configuration. So, but this relation will always hold, right? This is nothing but KCL on the device. And what is your, and another definition of alpha is defined as I common base current gain, right? So
IE or
output by input, and beta is defined as again output over input. Input in case of common emitter is base current. Input in case of common base is emitter current. Okay. You should understand these things. So now if I divide everything by IC, so what will I have? And this is nothing but 1 over alpha. This is nothing but 1 over beta. So what is my alpha? In terms of beta, it is nothing but beta over beta plus 1. Okay. So from this definition, if your beta is given as 60, so your alpha will be 60 over 61. And that gives you 0.9836. Okay. So this is a simple question. Then let's move to the next one. Base width modulation occurs in a BJT operation in what region? Anyone?
Data fusion, sir.
What region? Can you please say it again? I heard that you mentioned cutoff. Is it so?
Yes, sir.
So the answer is not correct. So we'll see why that is not correct. So base width modulation. Okay, let us first understand what is base width modulation.
So it will be forward active,
Why do you say so?
because in forward active the base collector region is reverse biased. So
Absolutely.
if we increase the reverse bias voltage, the
Okay,
depletion width becomes larger as per the PN junction property.
right.
So to tackle that, we, because we also know a property of PN junction that it tends to have depletion width larger at the site where the doping is less.
No, no.
And
Okay, let us not go to the remedy. Let us stick to the effect itself. So you are now
yes,
telling about the remedy, right?
so,
Not the remedy.
yes, sir. So due to the enlargement of that reverse depletion width, the effective base width reduces.
And how does that impact effective base width? Let's say let's get it reduced. What is the concern there? Firstly, tell me one thing.
So
Base
my
width modulation is a good effect or a bad effect?
basically, sir, for that effect, our IC cannot remain constant due to the
No,
what
it is a good effect or a bad effect for a IC designer.
I think it's a bad effect because IC keep on increasing, so we don't have the
So
linearity.
we want higher IC, right? We want higher IC. What is the issue there? Is the issue that IC increases is the problem? Is that the problem?
No, sir.
There is something deep associated with that. Okay. Yes, the effect is visible in forms of increment of IC, but that is not the overall picture. Okay. So let us go step by step and understand. So this is your emitter, this is your base, this is your collector. Okay. Now let's say this is your depletion regions. So there are two types of base widths. By the way, do you know what these junctions are called apart from EBJ and CBJ? There is a general terminology used that is called the metallurgical junction. Okay. That means the junction you create by metallurgy or physical junction. Okay. So this is your WB naught, and this region is called your WB dash. So WB naught is your metallurgical base width, and WB dash is your electrical base width. Fine. Now why electrical base width is important? Okay, before that, let us revise something. So what are the conditions on EBJ and CBJ for these modes? For cutoff, what are the condition?
Both to be reverse bias.
Fine. What is for saturation?
EBJ forward bias and
VJ
both are,
forward by
And CBJ?
is also forward bias.
And forward active, what is the issue?
EBJ forward bias, EBJ reverse bias.
And this is obviously the remaining case. Okay. So now tell me, let us take, we'll discuss about the reverse active mode a little later. Okay. So this is my, let's say, P type, N type, P type. Okay. So if my emitter based junction is forward biased, what are the possible modes of operation? This, right? Which can get possibly impacted by the base width modulation, because there we are concerned about the level of current. In cutoff, we by default get no current. So that is not of our concern. So obviously it has to be one of these two generally used modes of operation. Fine. Now, when my forward bias is there in case of a PN junction, how does the depletion width change? In case of forward bias, depletion width increases or reduces?
Reduces.
So depletion width reduces, right? So basically, by forward biasing the EBJ, WB dash increases. Okay, that is one fact. And also another thing, do we need high or low WB dash? We have discussed just a couple of questions back, right? What is the WB dash we require?
Lower WB dash.
Why?
To reduce recombination.
Fine. So we want a lower WB dash. But the main concern is, what do we want in our, what is BJT? What is the first level abstraction of BJT? If I ask you that, what is a BJT? What should be directly come into your mind? What is a BJT? First answer, what you should give?
Bipolar junction transistor.
That is the full form. What is this? Bipolar junction is a type. First thing you have to tell, it is a transistor, right?
Yes, sir.
So under any circumstances of BJT operation, my transistor action should not get violated. Okay, that is for sure. Transistor action, when will transistor action get violated? What is transistor action? Input port controls electrical property of output port, right? When my output port starts to dictate, then it becomes a, when output port starts to dictate its property, it becomes a resistor. Okay, because by applying voltage you are changing the current, that means it has become a resistance. It can be non-linear resistance, but it is after all a resistance. Fine. So this terminal is your forward biased. Now what will happen if I reverse, if I let's say forward bias this one. Let's say if I forward bias this one, what will happen in case of the depletion width? It will shrink. That is happened in case of saturation, right? So your WB dash will then again increase. So there is no point how your IC is getting affected. IC will get affected, but not to our disadvantage. That we will discuss why. But if it is forward biased, if it is reversed biased, then what will happen? My depletion width will start to increase, right? If my depletion width start to increase in the collector base junction, then my WB dash is reducing. If my CBJ VCB is your reducing, right? Or let's say the modulus VCB in reverse bias, I am increasing. That will increase the depletion width. That will reduce my WB dash. And what is the consequence of reducing the WB dash? My IB less recombination in base. That means IB reduces, but IE remains same. So to balance that, my IC will increase. Fine. So what can I see? I see that by controlling my VCB, I am able to control my IC. Should I be able to do that in if it is a good transistor?
No.
This is not desired for a good transistor action. And why I will explain. For example, this is your IC and this is your VC. Okay. So ideally, what do I want? Ideally want my curve to do like this. Fine. Let's say this is my saturation region. This is my forward active region. And somewhere here, let's say this is my cutoff. Okay. So now what can I see? If I keep increasing my VC, my IC will also start to increase. In this place, what was happening? Between 2 points, my VC increases, but my IC does not increase. But in this case, my IC is also increasing. So if I give you a IV characteristics of this sort, what is this? What is the element?
Constant current source.
That is a current source, right? Fine. So this is basically a this element is nothing but a current source or an ideal constant current source. Now what happened if I tell you something is like this? What is that? Anyone? Anyone? That is nothing but a current source in parallel to a resistance. That is a physical current source, okay? Ideal current source has a constant line, but physical current source has a tilted line. It has a parallel resistance across the current source. So this is exactly what is happening in this case. Now assume that you have a transistor. The small signal model, just for the time being, I am representing. I will discuss this in detail later. So for example, this is your beta IB and this is your IB. Okay. Let's say this is your emitter, this is base, this is collector. Fine. And you are at this point somewhere. So what will you expect? If you connect some load resistance, you want your voltage to get amplified, right? To that extent, the way this beta IB will change. Now think that there is a parallel resistance, this R0. Then how much current will go to this ZL? Will it be beta IB or something else? This beta IB current will then get distributed between this branch and this branch as well. So some of the current is getting sucked in by the R0. That means this voltage level V out will drop. That we do not want, okay? For amplifier applications, that is a disaster. We want my R out to be almost infinity. Remember, I discussed in my first session that what is the implication of having a transconductance amplifier. There my R out I want almost infinite, right? Because I want an ideal current source at the output. This is the same thing. So my transistor action is losing. In other words, my IC is increasing. Basically, if you keep walking on this line, you are not at a single plane. You are going up in a slope. Okay. So that means as you move along your VC, as VC is increasing in this direction, your current is also increasing. This effect is called base width modulation. And this modulation is enabled by the collector voltage or the output voltage. So I do not want my output voltage to control my output characteristics. Then it will just make a resistance. Fine. So this is what base width modulation is. Now you should have a question. So if at all my base width reduction is causing this issue, and in my forward active region my emitter base junction is forward biased, so emitter base junction is anyway reducing, so can I not replenish that? What do you think? By increasing the emitter base junction voltage. Did you understand the question? The question is, your CBJ is reversed bias, right? It is, if CBJ is your reversed bias, it is your reducing your WB dash. However, I have another thing, EBJ, that is forward biased. So that is making WB dash greater by reducing the depletion width at the EBJ junction. Can anyone comment? What is the issue here? Why can't EBJ help?
Because sir, if we consider the EVJ as a PN junction diode, because it is
It is
actually
a PN junction diode.
junction diode, so we know for the property of PN junction as for silicon diode, if it is 0.7 volt, up to after that, even if we increase the voltage very much, the current rises exponentially. So
Exactly.
voltage does not go beyond very much beyond 0.7 volt, because it almost becomes saturated
So
after.
basically what is happening, what Ankit is telling is that my current rises like this. Okay. So as soon as you reach this point is around 0.5 to 0.7 volt for a silicon diode. So whatever increment you have, your current rises very heavily. Okay. So essentially in this region, you are getting a characteristics that is parallel to the I-axis. What is this? This is nothing but a voltage source. You see that a current source is parallel to this, a fixed current, irrespective of any voltage across it. Similarly, in this region, it becomes a voltage source of around 0.7 volt. So after that, your depletion width does not reduce much. That is why we need to take care about the base width modulation effect. Fine. And that is the way to do that is to dope the region adjacent to the base in the collector lightly doped with respect to base, so that entire depletion region can be in the collector side. Even if you increase your collector voltage, the depletion width increment will be mostly in the collector side, so that your WB dash does not get affected. Okay. And there is another concept. If you have lines like this, so these all lines intersect at the same point, and this point is called your early voltage. Okay. Fine. So that is for your, so in saturation we have seen it cannot happen because any of the base width is getting reduced at the collector base junction. But what about this reverse active? So theoretically speaking, reverse active mode in the similar fashion can have your base width modulation. Fine. Because you think your emitter base junction is now reverse biased and your base is lightly doped with respect to your emitter. Fine. So most of the depletion will be in case of in your base region. So your emitter base junction, which is supposed to be the output side now, if you want to use it as an amplifier, is be controlling its own characteristics that is not desired, right? But we do not generally consider that because this particular mode, because in this region your amplification is generally lost, so you kind of use it as an attenuator. Okay. So if your attenuation is the main concern, then it does not matter if you have a R naught in parallel or not. Okay. So that is why this is also not considered. So forward active is the mode where we should be very careful about the base width modulation. Okay. So if that is so, now let's do some circuits on the BJT with BJT bipolar junction transistors. Okay. So how to this is this there will be some this will be some biasing analysis today. Okay. So biasing means we are only doing the DC part, no small signal involved until after a few problems. Okay. So how do we analyze this kind of circuits? There are two ways basically. One is your write the full nonlinear equations of I and V and use KCL, KVL and something we called NR method or Newton-Raphson method that is used to solve the nonlinear equations. Okay, what are the nonlinear equations? For example, your IC is IS exponential VBE by VT, right? This is a nonlinear equation. Fine. The same thing you do in your diode circuit analysis as well. So you have one approach where you write your full diode equation and then solve it numerically by Newton-Raphson method, because it creates a transcendental equation. One infinite exponential, basically, if I ask you what is this equation, can you solve this analytically? Can this be solved? Anyone? These are some of the important concepts you should know. Can this be solved? Can I find the value of x? Just tell me what you think. It may not be correct.
Yeah, we can
How?
by taking the log, taking x on the other side and then taking the log of both sides.
Can you get the value of x? Solving it means you should have a value of x, right?
Yes, sir, it is not possible.
And do this kind of equations are called basically transcendental equation. Okay. And why do you think it is not possible? This is not possible because your e to the power x is an infinite series of x. Is it not? E to the power x is what? 1 plus x square by factorial 2 x cube by factorial 3, right? You are equating an infinite series with a finite series. So that will never help you to solve anything, right? Because you do not know at what limit x your solution lies. Fine.
Yes, sir.
So that is the reason you cannot solve. Even if you take log, no, log of 1 plus x or log of x also has an infinite series expansion. So this you cannot solve. Similarly, any of the nonlinear equipments like transistors, diodes, you cannot solve them by full-blown equation. So what is the method we use generally? So method 1 is not acceptable to us. But you know your Spice simulators or your circuit simulators use this method to solve only. Okay, just a pointer. Spice is your simulation program with integrated circuit emphasis. Whatever the simulator, your cadence, let's say, then you have your H spice, P spice, LT spice, whatever you take, those all are numerical simulators and they solve these equations by means of Newton-Raphson method. You must have studied this in your nonlinear equations in your maths course in undergrad. The other method is you assume a bias and operation mode of the BJT. Solve it accordingly and then you re-verify the biasing assumption you made. Okay, for example, if I assume that my device is working in forward active and I solve the entire problem in assuming the forward active mode, and then when I get my answers I should always re-verify that whether my device is actually in forward active or not. Fine, this is called some kind of self consistency. So let me just copy this. So basically we have been asked to find out RC, only RC, IC as well. Okay, so first let us mark what is this current. This is your emitter current. This is your IE. This is your IB. And this is your IC. So what is this current? What is this current flowing through RC? Anyone?
Three volt by RC.
No, no. What is the current in terms of IC, IB, and IE? Is it also IC? Obviously, it is IC, right? Because there is no current flowing through this terminal. This is an open circuit. Your that node is you are seeing, right? That is nothing connected to that node. It is just VC. This 2 volts does not mean there is a battery connected. If it is a battery connected, it should have been signaled by some plus or minus. Fine. This is just the node potential. So it is an open circuit. So if you apply your KCL at this node, so it is only IC flowing. Fine. So what is the first step? Let us assume forward active. Okay. If I assume forward active and then my IE equal to IB plus IC. right? So if I take this loop, this KVL loop, so what do I see? IB times 50K, and there will forward active means base emitter junction is forward biased, and we are assuming silicon diode. That means this will be 0.7 volt. So there is a 0.7 volt drop minus 0.7 volt, and then guys, if you do not interact with me, then it will be very difficult to move forward, right? So please tell me, how should I proceed? I have written two equations and nobody has interrupted me. So what is the thing that we need to find? I need to find IC and RC, right? How can I
Sir,
find my IC? Yeah, please go ahead. Anyway, so your IE is basically IB plus IC, right? So IE, you know, is 1 milliampere. Your IB plus IC will be your beta IB. Beta is given as 75. So this is 1 milliampere and this is 76 times IB. So you know your IB is 0.01315 milliampere. So what is your IC? IC is nothing but this times 75. If you know your IC, then what will be your RC? 5 minus VC divided by IC. VC is given as 2 volts and IC you know 9868. 1 voltage by milliampere will convert it to kilo ohms. So 3 divide answer. So this will be your answer, okay? But what is the step left? That we need to check. We need to check our assumption of forward active, okay? So by the way, my emitter based junction is forward biased. How can I say that? I can say that just by looking at the level of current, okay? 1 milliampere in a silicon PN junction is a huge current. That means obviously my EBJ will have to be in forward bias. But what I need to check is whether my CBJ is in reverse bias or not. Okay. So this is your IB. IB, you know, IB is how much? 0.01315 milliampere. And this is the current flowing this direction, right? So what will be your this voltage, base voltage will be 0.01315 times 50. It will be minus 0.65 volt. Fine. And what will be your VE then? VE will be your minus zero point 0.7 volt less. So minus 0.65 minus zero point 0.7 is your 1.35 volt. So obviously you can see that in your NPN transistor, this junction is reverse biased. So that means it is obviously working in your, so your CBJ is reversed biased. So the assumption you made of forward active is valid. Okay. There is another way to check in case of common emitter amplifier, common emitter configuration. If VCE greater than VCE saturation, then also we call it in forward active. Okay. So what is VCE saturation? In silicon, it is generally 0.2 volt. So if this is your VCE and this is your IE, if your bias point, and let's say this is your VCE saturation. So if your VCE is somewhere here, so you can easily say it is in forward active. Okay. So have you seen or heard of this figure earlier? VCEsat equal to 2.2 volt. Anyone? Am I audible by the way?
Yes, sir, you are audible.
So can anyone comment on that? How do we arrive this figure? This first of all, let me ask you: do you at all, are you at all familiar with this in your circuit analysis that it is 0.2 volt?
Sir, I am not.
You are not? That is surprising. So okay. So have you gone through the lectures on large signal models? So we have three types of large signal model, right? T model, pi model,
Pi model,
and Ebers-Moll's
whole
model.
model.
So how does they come? I'll briefly discuss. Let's say if T model we discuss. So Let's say if you have this NPN transistor, okay? This is your emitter, this is base, this is collector. So how do they model this? They model the emitter base junction with a diode, and let's say that the current is flowing. Current is flowing in a fashion, let's say IF. The current is IF. Then the collector base junction, they model it as a controlled current source. Okay. So the controlled current source, why? Let's say if I give you a IV characteristics of this sort, let's say this is I1, this is I11, this is I12, this is I13, just a notation. So what is the element? What is the IV characteristics of this curve?
Current source.
Not only current source, it is a controlled current source, right?
Controlled current source.
So this element is nothing but your some alpha times I of 1, right? So this is a controlled current source. Similarly, in case of your BJT, you have this type of curves, right? Now, what if I ask you in this region, it just resemble to this one, this part, right? Parallel lines, straight parallel constant lines. And what are these positions controlling? Let's say IB1 is controlling, IB2 is controlling this, IB3 is this. So various values of base current is controlling the level of collector current. So this is basically a current control current source. Fine. So exactly the same way you model your PNP or NPN transit BJTs in this fashion. So this is called your T model or T large signal model, mostly used in common base configuration. Okay. Similarly, you have your pi model. Pi model is nothing but it comes directly from your T model. So you know your T model, right? Now let me tell you that it is used in common emitter configuration mostly. So I'll just draw my emitter this way. So this is my base, this is my emitter, fine, and I have a current source this. So this is my, let's say, IF, this is my alpha F, IF. So is that clear? I am not finished with the pi model. So this is the T model, right? This is the exact T model as of above.
Yes, sir.
Now what I do, let me connect two current sources. This is alpha F IF, this is alpha F IF, and remove this one. Is it the same? Can I add these two current sources and remove the IF, the earlier current source? I can, right? Because
Yes.
if I take this node, what was doing this node, what this collector node was doing earlier, it was injecting some current out of that node, that is alpha FIF. Now also it is injecting that current. This node was getting injected with some alpha FIF current. Now also this node is getting injected with some alpha FIF current. And this node, what is the current getting injected or out of it? This direction? Nothing, right? Entire current flow into this loop. So effectively my circuit remains same, right? So effectively my circuit becomes, so this is collector, this is base, and this is my emitter. So this is my IF, this is alpha F IF, and this is also alpha F IF. Now there are two currents in parallel. So can I combine them? Of course I can combine them. So let me just have this and this. So let me just have the current as 1 minus alpha F times IF, and this current is alpha F IF. Fine. This is my B, this is my E, and this is my C. So if I call this as my IB, I can simply replace this with beta IB. The same analogy that we have used for used while going from common base to common emitter. Okay. So this is why, how come I represent one current source and one diode with a diode? Basically, what is your diode equation? Diode equation is ID is equal to I naught exponential VD by eta VT, right? Minus one, later for the time being, let me ignore that. So this I naught, I am assuming to get it reduced by a factor of 1 minus alpha F. Basically, it is a weaker diode or a diminished diode. Okay. So this model from T to pi give you an insight of how your common base and common emitter gains should be and how it is different. So here if you note, we have used a alpha F, right? Alpha factor. That is the common base current gain. And here we use beta IB. It is just a representation of the same thing. Fine. So this is your celebrated pi model. Now what is your Ebers-Moll model? So basically we'll again start with the T model. So basically you had what? Let's say NPN. Let's say you have your forward active and you have your reverse active. Okay, and your NPN transistor. So you will have something like this. This is your N, this is your P, emitter, base, and this is your N or collector. So if this is your IF, this will be your alpha F, IF. Fine. Now in reverse active, what will happen? In reverse active, what is the forward bias junction? Anyone? In reverse active, what junction is forward biased?
Collector base.
So this collector base junction will have that diode, and the controlled terminal in that case is your emitter base junction. So let's say now the current is flowing R IR, and this will be alpha R IR. Fine. Now earlier models are focused only on the forward active region of operation. Fine. So to take into account the reverse bias also, what these two fellows suggested that we include this as well. I am just placing this in parallel to the forward active mode. So this is your IR and this will be your alpha R IR. Now depending upon the bias conditions, you can have any of them, right? For example, in your forward active mode, right? Your forward active mode, this will dominate and this will dominate. And what happens in forward active mode? The collector base junction diode becomes reversed biased. That means as if there is no such this reverse bias diode, because current will be very low, so we can assume it as an open circuit, right? So similarly, if IR is 0, then my forward this current will also be 0. So effectively you get back your forward active configuration or your T model, right? That is the idea behind this Ebers-Moll model. Now coming back to the question, why my VCEsat is 0.2 volt. So in saturation, what is the bias condition? EBJ is
Both are forward bias.
both are forward biased, right? So whatever we have discussed in the large signal model, we have understood that forward biases has to be replaced by some sort of diodes, right? So let's say this is my base, this is my emitter, and this is my collector. So this model is okay for saturation mode of operation. Both are replaced by diodes.
Yes.
So what will be the voltage drop across this? It will be around 0.7 volt.
Yes.
And what is the voltage drop across this? It is generally around 0.5 volt. Why? Because remember I mentioned sometimes back that your NC is much lower than NE. That diode check example we have used, right? We were seeing that the this your base collector junction was having a lower built-in voltage. That's why the cut-in voltage is also somewhat lower than that. So this is ideally how your by junctions will behave in case of silicon. Fine. Now what I do generally, so this base emitter junction you can replace it as a battery, and you can replace this also as a battery. So let's say assuming this is 0 volt, so this voltage has to be 0.7 volt. It is just the referencing, I am taking it 0. It is not necessary that it is 0, because the voltage difference between these two nodes has to be 0.7 volt. That's all. So then what should be my C if I connect it in this fashion? Can you see this should be 0.2 volt? If this is 0, this is 0.7. So this will be 0.5 lower than that. So this will be 0.2. What is the C node with respect to 0? It is just 0.2.
Yes, sir.
So this voltage is called your VCEsat. And that is why in case of silicon diode, you take it as VCEsat. So for common emitter configurations, the quick way to check if your device is in saturation is to see your VCE terminal. That means you don't need to always, because it is difficult for us to check the collector to base voltages. Why? Because all of my this is my common terminal, right? So this will be my input side, this will be my output side. So it will be easier for me to probe these points. So this is my VCE. So if this is greater than VCE SAT, so I can infer that my device is in forward active. Fine.
Yes, sir.
So let's move on to the next question. So let us draw the currents. So this is my IE, this is my IC, this is my IB. What is this current?
IC plus IB.
That is,
IE.
so please understand very carefully that the resistance connected to the collector does not imply that IC will be flowing through that. IC is the current that is flowing into the collector. That is this current. There is another node present here. So that is making my IE to flow entirely in that 10 kilo ohm collector resistance. Okay. So it depends on what kind of feedback I use. This thing is called feedback. What feedback is nothing but a connection between input to output. So what kind of feedback I use, depending on that, my collector current or the current flowing through the collector resistance may change. Be very careful about that. So now the question is, what is my VC? Fine. To find that out, I need to solve either one of the current, IB, IE or IC. So what is the current that I can solve easily? So to solve this, we need to find either of IE, IB or IC. What do you think is the current we should find? So this is the loop where we will use the KVL. Okay. Again, assume forward active. So what we have, 5 minus IE times 10K minus IB times 20K minus there is a potential drop of 7 volt, 0.7 volt minus IE times 2K is equal to 0. Is this KVL okay? So this 5 and 0.7 will give me 4.3 and other I can take outside. This will give me IE times 12K plus IB times 20K. So IE is nothing but beta plus 1 times IB times 12K plus IB times 20K. So 4.3 will give me beta is 75. So 76 times 12 plus 20 times IB. So that is how much? Plus 20. 4.3 divided by that is your 4.61 into 10 raised to minus 3 milliampere. Why? Because I am just ignoring the K. Okay, these all are in K. So that will give me another, that will give me the milli, and 4 by this much will give me 4.61 into 10 raised to minus 3. So what is my IE? IE is nothing but 76 times this. So this into 76 will give me 0.35 milliampere. Okay. Now once IE is known, so I can easily find VC. So what will be VC? VC will be nothing but 5 minus 0.35 milli times 10K. That is 5 minus 3.5 volt is equal to 1.5 volt. Okay. So A will be your right answer. But again, we need to re-verify this assumption. So if this is your, let's say this voltage is your how much? 1.5, right? 1.5 volt. So I need to check what is my VE. VE I can easily find. What is 2K times IE is this, right? IE is 0.7. So VE will be 0.7 volt. So what is this voltage difference? VCE is around 0.8 volt. So VCE is greater than VCEsat. That is around your 0.2 volt. So I can directly say that it is in forward active. And EBJ I know that 0.3 milliampere is a very high current. So that will make my EBJ into forward bias. So this forward bias, this reverse bias. So both of them combining giving me the sense of mode of operation in the circuit. Is that clear? So a couple of concepts. One is the current flowing through RC or the collector resistance should not always be your IC. Be aware of that. It can they can have in a feedback, such as in this case. And also you need to find out the correct loop in the circuit to calculate your whatever is required. And also you need to re-verify always that whether the assumption you have taken in the initial mode of operation is okay or not. Fine?
Sir, excuse me, sir.
Yeah.
Sir, can you explain last part of the calculation, sir?
Which part can you tell me?
Sir, VCE greater than VCE sat, no, sir.
So VC greater than VC set I have explained here, right?
Yes, sir,
So
yes, sir.
VCE sat for silicon diode is 0.2 volt. So basically it is this point, right? It is this point. So emitter is common, right? For the time being, let us assume that the emitter is grounded. Now, as you move along, with VCE is increased, so you will go towards the forward active, right?
Yes, sir, yes, sir.
So what you need to ensure that you need to have a point or a checkpoint before which you can say it is in saturation and beyond which you can say it is forward active. So we have found by this Ebers-Moll, using this Ebers-Moll model and the T model, we have found that for silicon junctions, this VEsat is around, where it is, this VEsat is around 0.2 volt. Okay.
Okay, sir, okay, sir.
Yeah. So that is why in this case we found out that VCE is 0.8 volt. So that is much greater than the 0.2 volt. So in this case, where will we be? If I have to point it out, so if this is my 0.2 volt, I will be somewhere here, right? So this is already in your forward active mode. So the assumption we have made in forward active is correct. So yeah, let's move on to the next part. So how do we solve these questions? This is a way of biasing and is called voltage divider biasing. Okay. So how do we analyze this kind of circuits? We are familiar with this form, right? Now, if anybody gives us this, we can easily solve. Let's say this is 5 volt, this is 5K, this is zero point 0.5 kilo ohms, this is minus 5, right? This is, let's say, VB, this is RB. So if someone gives me this form, so I can easily find out. Now, can anyone tell me how can I get from this form to this form? So I need to convert from the left hand side form to the right hand side form. So how do I do that?
Applying the voltage divider formula.
Please enlighten us how to apply the formula. It is not about formula, right? It is about the concepts. You should never tell that the formula is this. That was old days. Now you tell me the law is this. So formula you can anytime derive if you know the law. But if you do not know the law and remember the formula, if you forget the formula, you cannot derive back anything. You cannot get the law out of the formula, right? So can you tell me how to derive at that formula that you are talking about? So basically, I can draw this circuit. Let me just copy. So I can draw this circuit in this way. So this is your zero point 0.5 kilo ohms. Let's say 5 kilo ohms. This is 5 volt. This is minus 5 volt, and here I have one resistance, here I have another resistance, and this. So this is minus 5 volt, 2 kilo ohms, and this is 12 kilo ohms, 5 volt. Is this okay? Is this the same thing? Is this the same thing?
Yes, sir.
Now I want to replace this entire thing by a voltage source and a series resistance. What do I use? What theory in my arsenal I have to use this?
Thevenin circuit.
So this is nothing but your Thevenin resistance and Thevenin voltage source, right? So you need to find out the two nodes between which you should apply the Thevenin theorem. Let me consider this is the two node. Okay. Let me consider that this is the two port. So how do you find out your, so by the way, what is Thevenin's theorem? If I have a network, if I have multiple sources, if I have in this or this, I can replace the network with a voltage source and a resistance and then my network. The condition is that the network is a linear network. Okay. That means it is consisting of only resistances, controlled current sources, because these are linear elements of your circuits. Okay. Now tell me, how do I find my VTH? VTH is nothing but the open circuit
Voltage
voltage
across the load terminal.
looking into the terminal, not load terminal. It is the terminal between which you are applying the Thevenin. And what is RTH? How do I find RTH? Equivalent resistance looking into the terminal with all independent sources nulled. What is nulling a source means? Voltage source nulled means
Short circuit.
short circuit. Current source nulled means
Open circuit.
open circuit. Okay. So can I quickly find my RTH? RTH will be nothing but I short circuit this 5 volt and 5 volt. So it will be 12K
In parallel with
and 2K. So it will be 24 divided by 14, 1.714 kilo ohms. And what is my VTH? What is my VTH? So that understand that looking into the terminal means what? This is one terminal, this is one terminal. So this terminal is anyhow open, right? So I need to just find, and one of the port of that one element of the one terminal of the port is grounded. So I need to just find out the voltage here. This will be my VB or VTH, right? So I have what? This 12K in series with this 12 is, this is my 5 volt. This is 2K, and I again have a minus 5 volt of voltage source, right? I need to find out the potential at this point. So that will be what? That will be current. Current is what? 10 by 14 times. This will be the voltage drop across this 2K minus 5 to go till ground. So this will be my VTH. So 20 divided by 14 minus 5. So minus 3.57 volt will be my VTH. Is that okay?
Yes, sir.
Others, do you have any question in this? So we did find out the current through this. This is the current. Then we found out the voltage across this. This is the voltage. And then this voltage is from this point, but we want it from ground, right? So I need to subtract this minus 5 volt. So that part is done. That part is done here, right? So now my circuit becomes, so there is a VB. So this is my minus 3.57 volt. Uh, can you please mute yourself? Okay. So this is my then point.
கிளாஸ் போயிட்டு போயிட்டு இருக்கா
Okay. I need to make him remove. So this is minus 5 volt. This is zero point 0.5 kilo ohms, and I have 5K here. This is 5 volt. This is 1.714 kilo ohm, right? So this becomes your circuit. So now what you need to do, assume forward active, solve this, and then re-verify this. Okay. So that part I leave it to you. I will post the solution because time is running out. So I'll just yeah. So you have this beta equal to 100 that you need to use, right? So beta is equal to 100. Okay. So you just need to find out what is my ICQ and what is this voltages. You need to find out VC. You need to find out VE. Okay. And then you need to find out VCEQ. Fine. That much you can do.
Yes, sir.
Okay.
Sir.
So please do that, and let's meet next week. So next week we'll mostly do some of the BJT circuits and some of the MOS circuits. Okay. So I request you to please go through the lecture once, and also if you have any doubt in these assignments what I am solving, you can go through that lectures as well. Okay, and let me know in the comments or via email that what portion you need to re-explain. Okay, I may make a very short video explaining that, or I may provide some note or some reference. Okay, so good night to you all. Let's end the call here.
Thank you, sir.
Thank you, sir. Thank you very much.